the inferior lateral septal anterior, and each segment is supplied by blood supply, and it starts to observe how the blood perfusion is inside the myocardial area. It begins to compare the stress, test study, and of course, as we will discuss shortly, the gated technique for the SPECT or gamma camera is one of the acquisition modes available. Also, from the DTBA technicians, we use the DTBA scan, which is hydrophilic, meaning it travels along the same path as water in the patient's body. In this case, you want to see the glomerular filtration rate and assess kidney function, so you have the patient drink a lot of water before the scan. After that, the patient enters the machine and imaging begins with the radioactive material that enters their body and is excreted by the kidneys. This happens before the injection or at the beginning of the injection, where the kidneys start to light up strongly in black because they are inverted. Over time, you are essentially taking frames, with each frame taking about a second. You see the activity increasing, and you start to see the ureter and the bladder appearing. Eventually, in the last image, you find the bladder lighting up strongly, and you see the excretion depending on whether the patient is normal or abnormal in terms of kidney function, whether it is the right or left kidney. In this case, you can see how each kidney's function is performing and assess the technique used. So far, are there any issues, doctors? All right, let's talk about the generator again. This generator is what the technician refers to. Inside the generator, what do I have, doctors? I have alumina and molybdenum. These are present, right? Or am I mistaken about molybdenum and alumina? Now, when this generator comes into the hot lab where I work or perform the operation, they need to do something called quality control. What does quality control mean? It means you conduct a test to ensure that what you have coming out in this vial is pure technetium. Pure technetium. So, it will make a difference if a little bit of molybdenum comes out instead, because simply put, the energy of technetium is what matters. The gamma energy emitted is 140 kiloelectron volts. While if molybdenum is present, it emits energy above 700 kiloelectron volts. Imagine you have two radioactive materials, one emitting 700 and the other 140. First, this molybdenum not only emits gamma rays, but also emits beta minus particles. The beta minus particles can be absorbed in the patient's body, increasing the dose to the patient and raising the radiation hazard. Additionally, the 700 energy can create a scatter effect on the image quality. To ensure that the amount of molybdenum does not exceed 0.15 microcuries for every 1 millicurie of technetium, if I produce, for example, 10 millicuries of technetium, the amount of molybdenum should not exceed 0.15 microcuries for each millicurie of the 10 millicuries, which means multiplying 0.15 by 10 millicuries gives us approximately 1.5 microcuries as the total amount of molybdenum. Also, alumina, which is Al2O3, has a strong positive charge of +3. There is a problem with the binding between technetium and chemical compounds. For technetium to achieve binding, it takes on a positive charge. When it comes out, it has a specific charge. If you introduce something else in the same solution, like alumina, it starts to compete in the interaction, affecting the binding efficiency. This results in no effective binding between technetium and the chemical compounds. In this case, you need to verify that the radioactive material and its solution are different from the natural state. Therefore, we conduct two tests: alumina breakthrough and molybdenum breakthrough. The alumina or molybdenum provides poor emission quality, and the radiation dose limit is 0.15 microcuries per millicurie at the time of administration. How do I know this? With the dose calibrator. I will tell you now that alumina gives you poor emission quality because it affects the binding efficiency. The concentration is supposed to remain below 10 micrograms per milliliter. The method used is colorimetric. Now, what is a dose calibrator? A dose calibrator is a detector known as an activity meter. It measures the radioactive material for which I want to know the activity after performing the elution. I want to know the activity of this radioactive material, how many millicuries, how many microcuries, how many megabecquerels. So what I do is I bring something called an ionization chamber, which is essentially a cylinder with an opening. I start to introduce the radioactive material, which will ionize in all directions. The advantage of this setup is that it contains gas. And this gas will react in all directions, like this view. This is the sample setup, and the gas is around it. Your file is surrounded from all directions, and it starts to cause ionization between the photons emitted from the file and the gas, creating something called ion pairs. What does ion pair mean? It means negative and positive. This means that ionization occurs in air molecules, causing an electron to be ejected from the atom, making the atom positive and the electron negative. Thus, the negative and positive are called ion pairs. I then collect the charge from these ion pairs on something called an electrometer and measure it according to the number of ion pairs that will be formed. This activity gives me an indication of how much activity I have. The more the activity increases, the more ionization occurs, and the more ion pairs that are formed, which gives you a reading of how much activity you have exactly from the radioactive material. This is the idea of the dose calibrator. Now, I want to know the concentration of molybdenum. So you mentioned molybdenum repeatedly. There is a container or a thing called a lit canister, which is essentially like a cylindrical canister and has a thickness made of lead and is designed specifically. This thickness is adequate enough to effectively halt the energetic emissions from the radioactive isotope known as technetium-99m, a commonly used medical isotope, as we have previously discussed, to block or attenuate radiation effectively. And safely, you need protective shielding material, which is crucial in radiation protection. And this shielding has a material thickness or density. The greater the material thickness, the higher the amount of radiation you can stop. It is naturally understood that the material thickness required to stop 140 keV gamma rays is less than the thickness required to stop 740 keV gamma rays. So when I place this technetium that will stop at a 140, who will be affected? "740 is nice when I take this file with the LED canister and put it inside the dose calibrator. Will my dose calibrator measure 740 or will it measure 140? 740 is nice. So will my reading be an indicator of the amount of molybdenum or not? Yes, that's right. This is the molybdenum thorough test, where you have the LED canister present and you place the vial in it to start measuring. For example, I got 10 microcuries of molybdenum. Then you remove the LED canister and place the vial without it inside the ionization chamber and the dose calibrator. You measure and check your direction and see the ratio. Is the molybdenum ratio less than 0.15 microcuries per millicurie of technetium or not? If your direction is permissible, then that's fine. So this is the first test. I call it the molybdenum test. The second test is for alumina. Alumina uses a solution of alumina. You need to have a piece of alumina and then take filter paper, like we saw once in the previous video, and start putting a drop of it on the filter paper, which will give it a certain color. They make a comparison by carefully taking drops from the solution from the vial carefully onto another piece of paper and then compare the two colors. For example, here is your sample. The concentration they mentioned is referred to as part per part, such as a reference. What is the feature of the LED canister? The higher your concentration, the more the color starts to change. This means that your concentration should ideally be less than how many micrograms per milliliter, meaning less than that. If the intensity of the cooler is less than the intensity of the other, then you have passed the alumina breakthrough test, and everything is fine. There is no problem and no high concentration of alumina. However, if the intensity of the cooler leans towards the orange color, then this indicates that the alumina content is high in your sample. In this case, the test must stop, or the engineer should check for issues and refer back to the source. Another test that should be conducted is measuring something called pH. As you all know, the pH indicates the acidity of technetium. The pH usually ranges from 5 to 7. This is done using a pH meter or pH strips, where you place it in the solution and observe the color, which serves as an indicator of the pH value. The value of the generators and the basic quality control tests. Well, now I want to focus on this case a little. I brought the technetium and made sure that there are no issues with it. What should I put this technetium on? What's the next step? What step should I take now? I have now prepared the technetium for labeling. What should I put it on? The chemical compound. Let's assume the chemical compound is for MDP, for example, or maybe whatever. What is the substance? Well, I have three possibilities. The first possibility is that technetium with molybdenum undergoes labeling, which is not a problem, resulting in something called a labeled compound. A labeled compound has no issues, or if technetium is not bound, it remains free technetium. For example, if I have approximately 100 atoms of technetium and 9 atoms are associated with MDP, I have 10 atoms. For instance, 10 particles or 10 particles that are not associated with anything, so I call them free. It is possible that while you are preparing, an issue generally occurs with technetium. This issue is called hydrolyzation. What does hydrolyzation mean? It means that after you place the technetium in the MDP, while you are preparing, the technetium should be diluted thoroughly in a saline solution. You put your technetium in the chemical compound, which is in powder form. Sometimes there may be dissolved oxygen molecules in the saline. This oxygen usually causes hydrolyzation of the technetium. What does hydrolyzation mean? It means that the technetium should be able to associate with a chemical compound undergoes a process called reduction. How does this reduction happen? It occurs with a substance that is present in any chemical compound you purchase. What is the chemical substance that you will use? It is the pharmaceutical chemical that you will use. The function of stannous chloride is to perform reduction on technetium, to make it suitable for binding with the chemical compound. After the reduction, if there is oxygen present, the oxygen will oxidize the reduction, which is called oxidation. This oxidation affects technetium, leading to a process called hydrolyzation. Reduced technetium means technetium that has been reduced but has undergone hydrolyzation. As a user today, I do not want free technetium, nor do I want hydrolyzed reduced. I only want this labeling. However, it was stated that the efficiency of this labeling should not be less than 95%. So I am conducting a test. Okay, I am conducting a test using something called thin layer chromatography, TLC. This test tells you the ratio. of the compound or the ratio of the labeled technetium to the chemical compound in your solution. So how does it work? They use something called TLC paper. What is TLC paper? It is thin layer chromatography paper. This paper has a specific property that when you place it in any solvent, that solvent starts to migrate through it and moves to a certain area, traveling a certain distance. This distance depends on various factors. For example, you might find that the solvent stops here, or here, or here. So based on what does it stop? Based on several things. First of all, the solvent. What is the molecular weight? 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 What we do is we take the strip from the substance and we put a drop of our substance here. I perform an immersion for TLC paper into a solution, which I call a solvent. Then the solvent will move and bind to the point where technetium is present and start to move a certain distance. In my test, I can use something that tells you, for example, if you want to use something to check on a specific component, utilize a method known as, if you want to work with the hard component, utilize it with the solvent. In this context, the solvent varies depending on the type of radiopharmaceutical. Let's say I have saline and acetone. This is your solvent, and here is the TLC paper. I place a drop here on the origin area. What happens is that the saline starts to move inside the paper and begins to take the technique. Observe, this point contains three things: the free, the hydrolyzed, and the labeled that I mentioned earlier. The saline has the ability to bind or make a binding with the labeled, such as the saline has the ability to bind or make a binding with the labeled. The free labeled domain and the free are certainly wonderful indeed. So if they happen to tell you that the saline will come out, it will be united with the free label and will move towards the solvent front area, eventually reaching the end of that distance. So, who will remain under the hydrolyzed? Great. When we use acetone, it will only carry the free and leave the hydrolyzed and labeled components below it without binding to them at all. All right. You have TLC paper that you can cut into two separate pieces. You cut the TLC paper from here and here, and now you have an area where the top area had the free and the label, and the top area had the free, and the bottom area had the hydrolyzed atar, and the bottom area had the label. So, what do you want to tell us? I want to tell you now that it's as if I have done a separation or segregation of the contents of the drops I took from the technician's file. I have a part present at the solvent front and a part present in the origin area. The part at the solvent front can be measured with a dose calibrator to know its activity, while the part retained at the origin allows me to know its account or activity. The same idea applies with another solvent. I will measure at the solvent front and at the origin. In the first paper, I can determine the amount of hydrolyzed, and in the second paper, I can determine the amount of free. So, if I know the percentage of free and the percentage of hydrolyzed, I can simply add them together and subtract from 100 to get the percentage of the labeled amount. Let me repeat that. The labeled amount, right? Okay, good. This is called TLC quality control, or thin layer chromatography. This is to determine the labeling efficiency that occurred using two different solvents. I use TLC paper and Frank solvent, and I can use pure TLC solvent that can interact with one type or with the three types, whether hydrolyzed or labeled, depending on the type of solvent and the type of radiopharmaceutical. Then I start with a specific procedure to determine which will rise and which will remain at the origin. I cut the paper and begin to measure the count above and the count below, or the activity above and the activity below, and calculate the activity of the free or the activity of the labeled. Quality control tests, quality control tests, quality control tests. Also, a set of tests is also conducted for quality control regarding these tests, with the calibration still in progress. There are periodic checks, some are daily and others are quarterly. I have a set of 4 tests: accuracy, consistency, linearity, and geometry. What are these? I use something called a calibration source. What are the sources of radiation? They are sources that emit radiation with long half-lives, such as cobalt, barium, and cesium. These are 3 stable sources of radiation. Or they use different sources, 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 different sources. In that case, at what time do you have a device in nuclear medicine? You want to ensure that it is measuring the activity you are monitoring correctly. What should you do if it is not accurate? I will obtain a known calibration source for activity. From where? From the nest, which is the measurement and calibration. These are the known calibration sources for activity. There is no game or alteration involved. This is something that comes from the factory. I know the activity levels for cobalt, cesium, and barium. These 3 calibration sources are available in any New York medicine department. So what do I do after I get them? I start measuring, comparing the actual readings with the expected readings. The variance between the 2 readings should not exceed 5%, plus or minus 5%. This is called the accuracy test. I measure for cobalt, cesium, and barium. The first one is approximately 5%. This is called the accuracy test for cobalt, cesium, and barium. I measure the energy of cobalt, cesium, and barium. The energy of cobalt is 122 kilo electron volts, while the energy of cesium is 662 mega electron volts, and the energy of cobalt 60 is 1332. I use 3 different radioisotopes because they have different energy levels. I check the efficiency of the dosimeter or the activity meter in low energy, high energy, and medium energy. I obtain the expected value, which is based on the decay sheet. Today, the theoretical activity of cobalt should be 2.4 millicurie. Did it measure 2.4 on the dosimeter, or was it less or more? If it equals, then the variation is 0%. What is the allowable variation? I do this for cobalt, for cesium, and for cobalt 60, and I do this for barium. Some say you can allow this variation up to 10%, which is fine. This is the acupuncture goat medicine and goat